This is an example. So this has applications both in linear programming, and by extension, it has applications in economics, in finance, in transportation or logistics. And so look at what we've done here. Again, we're using row operations. So we, for example, add one equation to the other equation, or we multiply one equation to another equation, or we multiply one equation with some number and then add it to another equation. If you do this by hand, it is very cumbersome. Okay, the linear program example I showed you was very trivial. We only had two equations. Here we have three, and even in this case, you have to do a lot of addition, subtraction, multiplication to eventually find the roots. So here are the roots: x is equal to 2, y is equal to -1, is equal to 3, and it's called reduced row echelon form because look here. What happens is that in order to know that you've actually found the solution or the roots for all three equations or the roots for all of these variables, is you get this form, you get this diagonal form. Can you see how we have 1 across the principal diagonal? When your matrix looks like this, let me zoom in. When your matrix looks like this, where you have 1 in the first row and 0, 0, then 1 in the second row in the middle. This diagonal, basically, once your matrix looks like that, you can then substitute the values back into your equation. So for example, x stays 1, 2 becomes 0, 3 becomes 0, and 9 becomes 2. This is how you would have found the roots of your roots of these of all three equations. And again, I said this is important. Why? Because let's say you have multiple models, like in financial modeling, for example. We said that a model is supposed to be a representation, not necessarily technical, a precise representation, but a representation nonetheless. So models, which come in the form of equations most of the time, if you were to find the roots of those equations, then you would have understood why this model behaves a certain way. Okay, the model, the equation for force is one example. Force equals mass times acceleration. Okay, so if you're able to find the roots, then you can get to the essence of the model, and then you can use that for regression in machine learning. Okay, so in the real world, you have to handle multiple models at the same time, and linear algebra gives us techniques for that. Now, I said earlier that this is very cumbersome to do. Like, you have to do a lot of manual arithmetic, which brings us to Python. With Python, we can't solve systems of linear equations like this almost instantaneously. So we don't have to do this by hand, but we still want to have the capability to do it. So what we will do is we can do linear programming in a large sets of equations, on large sets of constraints with a library like NumPy. Okay. Anyway, this was supposed to give you a glimpse into the first part of the first, let's say, half of linear algebra, which I said is systems of linear equations.